Okay, so chapter 5. So before chapter 5, we didn't really have any tools to solve problems using non-ideal gases. So we weren't really able to relate PV and T because obviously a non-ideal gas, the ideal gas law doesn't apply. So this is when we started to question whether the gases we were dealing with were ideal or non-ideal. And in order to know if the gas is ideal or non-ideal, you want to calculate RT over P. So for a monatomic gas, if it's over 20 liters per mole, then it is ideal. And then if your RT over P is greater than 5 for a diatomic gas, then it is also ideal. But if it doesn't meet either of these two criteria, depending on what whether it's monatomic or diatomic, if it doesn't meet those criteria, then it is non-ideal. And if you determine that it is non-ideal, then you have to use either equations of state or the compressibility factor in order to relate PV and T. And the compressibility factor is basically lets you use a modified version of the ideal gas law. So it that Z value, the compressibility factor, accounts for how far away from ideality you are. So the Z value, in order to find it, you're going to have to calculate a reduced pressure and a reduced temperature or a reduced volume. And you'll be able to solve for Z and then whatever other variable that you were asked to solve for. So to find these reduced values, to find the reduced values, first you have to start with finding TC and PC. You'll be able to find these in the appendix or in the test booklet that you're given on test day. And each specific component has a different TC or PC value. So based on whatever component you're working with in that system, you are able to find the TC and PC and then calculate your reduced values. So reduced pressure is going to be equal to P over PC, and then reduced temperature is equal to the temperature of the system over that component's critical temperature. And then VR is equal to V hat over VC ideal, or V hat over RTC over PC. So you need either both of these, so TR and PR, or just VR. And then K's rule, so say you have a real gas mixture, then you have to apply K's rule. So that basically just says that you are able to use a weighted version of your TC and PC values in order to solve for your reduced values. So say you have components A and B, then the mole fraction of A times A's critical temperature plus the mole fraction of B times B's critical temperature is going to equal your TC. And then same for pressure, YA PCA plus YB PCB. And then you get your reduced temperature the same way you did up here. So it would just be T over your modified TC, and then P over your modified PC. And then here is just written out the steps to finding the compressibility factor. So first what you would do is find your TC and your PC from the appendix, and then calculate your TR and your PR. If it's a mixture, make sure you account for that. If not, you just straight up use the PC and TC value given from the appendix. And then if you're dealing with hydrogen or helium, then you have to add 8K or 8 ATM to apply Newton's correction. And then you use the plot on page 208 or plots on 208 through 210 in order to find the Z factor. And then once you find your Z factor, you can use this modified version of the ideal gas law in order to find whatever variable you're looking for. So if you already had your P, so if you used your PC and your TC, you obviously already know your P and your T value. So maybe you're trying to find the number of moles or the volume, or if you already had your volume, then obviously you already have your P and your T. You could be solving for your molar flow rate.